So we're finally up to that fundamental theorem of algebra we've been talking about for most of the year. I'm going to run through sort of an explanation of it. It's not a full-on proof, but it's using the ideas we've been building up to in this section, or this chapter. And I think it's going to convince you that this must be true. At least that's the goal. And I would pull this up on your notes and kind of follow along, pause the video as you need to, and just kind of read through until every piece of it makes sense. So the first thing is the factor remainder theorem. So if I have some polynomial f of x, okay, some function's polynomial, and I divide it by some factor, x minus something, x minus 2, something like that. If that remainder comes out to be 0, we know that that thing I divided by is a 0 of the polynomial. That's what the whole factor remainder theorem was about. So I take that one step further, and this is a new theorem. It's in this section, in the front of it's in the front of the section of the book if you want to see it in more detail. But it's called the linear factorization theorem. So assume that we kind of brute force our way through this, and we try an infinite number of possibilities until we find all of the possible values for n that give us a remainder of 0. However many factors that comes out to be. All right. Well, it turns out that you can write any polynomial as the multiple of all of its factors times one another. This is just kind of reiterating what I said a few minutes ago. You could take the polynomial f of x, and if you had found all of the zeros, you could go through and divide f of x by each one of those and get a remainder of 0. And that would show that they are, in fact, zeros of the function, the polynomial. And these numbers, n1, n2, and 3, and so on, they're complex numbers. So this does allow for things like 1 plus 2i being a solution. So keep that in mind, that this works over the complex numbers. So the conclusion, any polynomial can be written as the product of its factors in this form. And I'll go ahead and reveal the rest. So kind of like what I showed you before, the function is x minus one factor times x minus another, and so on, where these values, these numbers here, they are the zeros of the polynomial, and they're complex numbers. One last thing about the fundamental theorem of algebra, if you think about how many factors you would have for like a third degree, x cubed would have 3 separate factors, or a function that starts with x cubed. So the reason the degree is the number of solutions, you would have x times x times x to get x cubed. If you think about all the factors, the leading coefficient or leading term, it's going to be x to the power of however many factors or zeros that you have. So it's another little piece of this that's kind of in the background. It's something we usually go by and accept to be true, but that's sort of in here is why. It's not fully laid out, but that's kind of something you can interpret there. So now let's apply the theorem. We've got a function here that's x cubed, so there are going to be 3 zeros. And we'll go ahead and, kind of like I usually do, just get ready with my box with 3 spots ready to go. And we're going to see what they are. So I'm going to do this fully by hand. Everything in this section I'm going to do by hand. Let's start with the possible rational zeros. So I could have factors of 29, which are 1 and 29, the positive and negative versions of those, over factors of 1. So basically, positive and negative 1, positive and negative 29. Those are my possibilities. Now, for the sake of time, I'm going to cheat a little bit. I already know negative 1 is going to be one of these. But we can apply some of our other tests. And this one wouldn't be too bad because there's only 4 possibilities for rational zeros. So we really only have to do synthetic division a few times. And you're probably going to start with 1 and negative 1 anyway. I start with positive 1 first. When that didn't work, I moved to negative 1. And that would probably be your normal process. So we'll do synthetic division, see if we can get this to divide out. And just run through quickly. All right, that's going to come out to be 0, so that is a 0 of my function. So negative 1 that's one of my zeros, or one of my solutions. Okay. So now, from the factor remainder theorem, this factor times x plus 1 would equal the original polynomial. So that means I can continue breaking this piece down. Okay, well, this is going to be 1x squared plus 10x plus 29. if I try to find factors of 29 that add to 10, that process is not going to go very far. We already know 29 is prime, so 1 in 29, that's the only way to get it. And there's no way to make that add up to 10. So this will be a good candidate to use your quadratic formula on. So negative 10 plus or minus the square root of 10 squared minus 4 times a times c all over 2a. And let's reduce down and see what we can get here. So negative 10 plus or minus the square root of 100 minus 116 all over 2. So negative 10 so negative 10 plus or minus, this will be the square root of negative 16 all over 2. So this will be negative 10 plus or minus 4i over 2. And I'm just going to bring it down so I've got a little more room. Both of these can be divided by 2. So let me do it the proper way. I can take a 2 out of negative 10 and 4. So that leaves me with negative 5 plus or minus 2i. So if I distribute that, that's my negative 10, that's my 4i. And those 2's reduce out. So negative 5 plus or minus 2i, those are my 2 remaining solutions. And just to make sure that's clear, I'm going to write those separately up here. And that should do it. Those are my 3 solutions. Now, as always, we took a polynomial and broke it into its solutions, so let's take our solutions and build them up into polynomials. Now, you've already done this in Algebra 1. I think we did it earlier in this chapter. We got one extra challenge here. We need the function to go through 1, 8. That point needs to be on the final result. So don't worry about this part yet. Let's just get the polynomial first, and then we'll deal with that piece of it. So if negative 1 is a solution, that means x plus 1 is a factor. And if 2 is a solution, x minus 2 is a factor. And if x plus I, or if I is a factor, then negative I is also a factor, or solution, sorry. And the way to think about that, if we were to get I as a solution as we did here, that's going to happen from taking the square root of a negative, which comes from the quadratic formula. So if you end up getting I in your answer, that had to come from quadratic formula, which has plus or minus in front of the radical, you guarantee to have a positive and a negative version of that complex number. That's always going to happen. It's called complex conjugates theorem, but that's why it's happening. So I'm guaranteed these are actually my 4 solutions, even though there were only 3 listed. Conjugates always come in pairs. So I and negative I are both solutions, so those are my factors. So what I'm going to do is kind of tournament style, since I've got 4 of these, and we'll do these 2 together and these 2 together, and then the winner moves on. So x times x is x squared. Outside would be negative 2x. Inside would be x. Last would be negative 2. X squared minus x minus 2 is the combination of these 2 together. This one is going to be, let's just kind of group those. X squared minus xi plus xi minus I squared. So x squared comes down, these 2 add to 0, and I squared is really negative 1. So negative 1 is really 1. Now I need to multiply these 2 results together. So x to the 4th plus x squared. Actually, I take that back. I'm going to do these 3 times x squared first. It really doesn't matter. I just think that might be a little bit easier. So x squared times x squared is x to the 4th. Negative x times x squared is negative x cubed. Negative 2 times x squared is negative 2x squared. All right, now I'll take each one of these times 1. So x squared times 1, and I'm going to line them up. Negative x times 1, negative 2 times 1. Put it all together, we get x to the 4th minus x cubed minus x squared minus x minus 2. So that's my function. F of x is that function right there. So I want to find out what happens if I put in 1 for my function. So if I were to put in 1 here, I'd get 1 to the 4th minus 1 cubed minus 1 squared minus 1 minus 2. 1 to the 4th is 1. 1 cubed is 1. 1 squared is 1. 1, 2. So 1 minus 1 adds to 0. I'm just going to scratch those. Negative 1 minus 1 more minus 2 more, that's negative 4. So as is, f of 1 is negative 4. Now I need to keep the same zeros, but I need for f of 1 to become positive 8. So there's two things that can happen here. One's completely wrong, so don't ever do it. The other one's the right way to go. One thing you could do is just add 12 to this, because if I added 12 to negative 4, I would definitely get 8. But if I add something to the end of this polynomial, well, adding a number to a f of x, so let's say we do this. Let's say it's f of x plus 12. Well, adding a number to your function is going to raise it up 12. That's going to really mess up these zeros. And I'm going to show you this. I'm going to do a visual of this at the end on Desmos so you can see it happen. So that's not a good idea. We shouldn't do that. We could stretch this thing so it has the same zeros, but it gets stretched to be the right point. And it would also need to be flipped around. Now, algebraically, just think about what's an easy thing to multiply negative 4 by to make 8? And the answer would be negative 2. And it's algebra, so whatever you do to that side, you got to do it over here. So that's giving you a recipe right there. If you take that function, f of x, times negative 2, that should do it. So that's what we're going to do. F of x, your new function. Take the function that we came up with. We're going to multiply all of it by negative 2. So we're going to get negative 2x to the 4th, positive 2x cubed, positive 2x squared, positive 2x, and then finally positive 4. And just to confirm on Desmos how this is going to work, here's my function. Let me put it in projector mode so it's a little easier to see. Take these out of here for now. So there's my function, the way it originally was. F of 1 is at negative 4. So what I was telling you is if you add something to the function, just add a number to the end to make it go up to what you want, well, that slides, oops, let me make sure that you can see that part. That just slides the whole thing up or down, so it's no longer going to have the correct zeros, and that's a problem. Another option is to multiply it by something. So let me see if I can get it back to 1 here. Get it back to where it was. So there's the original function. If I multiply this by something, it doesn't change the zeros. It stretches the graph, or flips it, or shrinks it. It does a lot of things like that, but the zeros never change. You're still seeing those two real zeros in the same spot. So if I multiplied it by negative 2, and went off the screen a little bit here, but 1 is going to be 8 for a value, and there we go, if I can stay. So that's going to check out, that's going to be good. All right, one final example. I'm going to find all of the zeros given one of my zeros. Kind of classic algebra 2 problem. But the zero you're given is a complex one, so it makes it a little trickier. Now, knowing that that's a zero, the conjugate is automatically also a definite solution, guaranteed, no exceptions. Now, there's a couple approaches. You could make these factors and FOIL them together and then divide them out. You would end up exactly with the last zero, or last zero that way. So that's one way to get there. I tried it and found it to be a little more involving, so I think what I'm going to do is synthetic division. And you could also do long division, that'd be fine. This is one of my zeros, so I can put it in the box. Missing an x squared, so put a 0, negative 2, and 4. All right, so let's play the game and see what happens here. 1 comes down, 1 times 1 plus I. 1 plus I comes down. Now it gets fun. So I'm going to have some scratch work over here on the side. So 1 plus I times 1 plus I again. Well, that's going to be 1 plus I in the middle plus I squared. So 1 plus 2i minus 1, because I squared is really negative 1. So that's just going to be 2i, because that 1 minus 1 goes away. So now this is negative 2 plus 2i. All right, I'm going to get rid of that so I can continue in that spot. I would encourage you to just do it on scratch paper. 1 plus I times negative 2 plus 2i. FOIL that out. 1 times negative 2, 1 times 2i, negative 2 times I, and plus 2i squared. So 2i minus 2i adds to 0. 2i squared is really negative 2 because I squared is negative 1. So that's going to be negative 4, which is good. We were expecting it to be a 0, and this had to end up being 0 for remainder. Okay, so now I've divided one factor out of a polynomial. I can take what's left, the quotient, and divide more out. So 1 minus I. All right, this won't be as bad. 1 comes down. Now it's 1 minus I. Add those up, you get 2, because those cancel out or add to 0. All right, 2 minus 2i. And now that adds to 0, that adds to 0, so that's good. So x plus 2 is my final factor, set it equal to 0. And x would have to equal negative 2, and that's my final solution.